but we cannot find that something has bound to the crystal, and we may need to do many experiments. And all of that is extremely expensive, and protein crystallography, the crystals which can be used in protein crystallography are extremely expensive. And they are much more expensive than any diamond in the world if we calculate their price by volume or by size or by weight. So how to define high throughput at the beamline? It's not the beamline which allows you to collect, or home system which allows you to collect 1,000 of data sets, but it's the beamline which produce as many as possible biological results. And deposit is not necessarily biological results, but a series of deposits, or sometimes one deposit, or sometimes a protein structure together with other data can produce very, very interesting biological results. It is true that many structures we can solve in 5–10 minutes, but sometimes there are so-called difficult structures. And they are difficult due to multiple problems, but they may be worth to pursue. And for example, we may have a single crystal which is not sufficient to obtain complete data set. So we can use more than one crystal and merge the data. We may have insufficient phasing signal, insufficient or anisotropic diffraction limit, internal non-isomorphism in the crystal, macroscopic problematic macroscopic order, for example, twinning, and we may have difficulties at the late stage of structure solution when we think that we really have solved structure, but we cannot refine, we cannot get reasonable R crystallographic R factor. And part of the models may be poorly ordered, and we may have complex disorder resulting in poor refinement statistics. And we should be able to really detect of all these problems easily. This is the most important, that if something does not work, you have to have ability to find what does not work and try to fix the problem. And this is the strength of HKL, not quality, not R factors, not the quality of the data, although I still think it's superior to any packages, but I am biased, obviously. But the most important is that we know almost always why we cannot solve the structure and what we should do to get the structure. And here I am putting diagram of HKL3000, and HKL2000 is somewhere here, yes? So HKL2000 allows you to define the problem, to process, to reduce the data, and to get HKL FN sigma. HKL3000 interacts with other programs. It has there is some development, but it also interacts with other programs. And it uses, for example, shell XB, or to find the sites, heavy atom sites, phasing sites, and it uses MLFair and sometimes other CCP4 to phase and do solvent flattening, and it uses ARP-Warp or Buccaneer or some other programs to build the model. And usually, when we are collecting data at the Beamline, we are looking at the map. We do not look at the data, we look at the map, because everything can be done extremely fast. Sometimes people complain that they cannot index the data. And this is the opening of the HKL2000. When the system asks you to select a detector that describes your experimental site. And this is your experimental site, and here is, for instance, ADSC quantum 4 detector at particular beamline. Here is 19 ID with quantum 315 at first quarter of 2006. This is some Mars 345. So you can name the site as you want, and afterward you can only use the site. If you do not know the description, if you do not have dev site file, you have to ask synchrotron Beamline to provide that for you. The other possibility is that you can create it by yourself by clicking New Site, and in that case, program will ask you for a detector, type of the detector, and type of the goniostat. Or you can ask HKL Research to provide you with a site. Now, what is in the site configuration? Yes, why it's so important? First, you have the detector. Yes, the information about the detector is in the program, and you have to say what detector is used. And this is ADSC quantum 4 transformed data, not raw data. Usually you're getting transformed data. This is the position of the beam on the face of the detector, the misalignment of the incoming beam, information that you collect the data at the synchrotron and polarization of the beam, misalignment of the detector, and alignment of the goniostat axis, direction of 2 theta, and blind region on the detector. The most important part is who saved the site, when, and what was the chi-square. And you see that here the site is suspicious, because the site was not derived from the processing of the data, because we do not have chi-square. We only have name, Wladek, it's me, and the date when the detector was, when the site was saved. Afterward, we have to provide the information, where is the data, and we are doing that with the directory tree. I will do that in a moment in the real time. We have to say where we would like to have processed data, and we are clicking Cloud Data Set. The program is looking for a particular type of the template. Remember that if the program cannot find the expected table, you are getting information that there is nothing. In that case, you can click Show All Files and define the template from that. So you see that if you have new detector, or your detector has different template than what program expects, you can change it here. Yes, you have here predefined file template, which is star.img, and as you see that it has found that in the directory is 250 files of with this template. First thing what you are doing, you are clicking Pick Search, and the program finds the peaks on the single diffraction image, and you can click Index, and what you are getting 14 Bravo lattices, and here is the distortion index, which describes how much you have distorted the unit cell to force that into particular Bravo lattice. And always you can have primitive triclinic, and red is something which is very unlikely, dark is possible. When we have something like that, we probably do not have the perfect type. Yes, it's enough that you have wrong position on the beam, and it creates problem. And if the difference between the real position of the beam and the information inside file is larger than the half of the distance between spots, yes, a second. If it is larger than half of the distance between spots, you may have misindexing. Yes, so here it's relatively easy to misindex in one direction because the distance is relatively small. After refinement, you should refine always in P1, and after refinement you may check space group, and you see, or Bravo lattice again, that it's probably primitive monoclinic. Now there is very, very important thing, that at that point we cannot find the space group. Yes, the space group can be found much later. Yes, we only can suspect certain Bravo lattice. If program rejects too many reflections, you can change rejection criteria. Yes, and rejection criteria, it's all described in the manual, is variation of the background, multiple spots, and things like that. And it's especially useful if you would like to remove some ice rings. You can use, program has very sophisticated strategy, but remember that the goal of the strategy is not to minimize the use of the instrument, but to maximize what you can get from the one crystal. And here it's the evaluation of the radiation decay, and you see that in the frame 175, if in the first frame you have resolution 2 angstrom, in frame 175, the resolution will be 2.3. So you see that you would like to maximize everything what you can get from the crystal. Here is integration. Integration is very fast, and scaling. Yes? And scaling, here you have tremendous anomalous signal because it's selenium crystal. And you can find the space group by looking into space group diagram, which is here, space group. Yes, and you are getting this suspicion, what is the real space group? And here are, you are getting Glauer class diagram. You have two possibilities which are a little complicated. What is the most important? That you can get feedback of possible hardware, sample, or experimental problems. And here you have twinning. Here you have goniostat, which is misaligned. And here you have incomplete low-resolution data. All these things may create problems during the structure solution. So you see that here is an example of very poor diffraction images, which still created structures. And the one very, very important thing that these days, HKL2000 is a pipeline component. So we know everything from the cloning to the structure solution, and we can easily identify suspicious density into the map. So we have something like nervous system which connects everything to get the structure. And as I told you, we are interacting with several programs which were done by other people, ShellXD, ShellXC by George, Sheldrick, Zbyszek did MLFerent, so it's ours, but Resolve was done by Tom Terwilliger, and so on. So first we have to set up the project. And I will switch now to the real exam. And I would like to show you the processing from simple data, simple machine, but processing and structure solution from anomalous signals from surface. I will go to the project and will load project, not to, and you see what you have here. I will remove this file. What you have here is a sequence. So sequence will allow you to figure out everything later. And you have data, already predefined data. So I will display immediately, will do peak search, and will index the data. Yes? And you see that you have very good site file. Yes? For I-center cubic, you have green with 0.1% distortion. So I will fit all, and I am refining first in P1. You have perfect chi-square to good chi-square. And Brave lattice, you have even smaller distortion for I-center cubic. We are applying, we are doing few refinement, and we integrate the data. And now the program is saying, okay, would you like to overwrite X files? Yes, because I already processed this data, so they are there. So I'm writing yes. The other possibility is to go to another directory. And as you see that you can observe everything, all parameters like mosaicity, crystal, chi-square, during the processing. And processing is very fast. Yes, remember that processing is very fast. If you complain that processing is slow, it's not a problem with program. It may be a problem with your computer or with, most likely, with your disk. How fast is your disk? If your disk is on the network, on the slow network, the processing will be very slow. We process 265 data images in something like 1 minute or so. Now I will go directly to the right space group for insulin because I do not have too much time, and I will scale data. And what you have here, immediately you see from scaling that you have complete data set. There is 0.18% of data marked for rejection. Nothing was rejected. And you have 5% are matched. Why this 5%? You may say it's too large, yes. It's relatively large because you have anomalous signals from surface. And we will apply absorption correction, and we will do rejections immediately, and we will see what will happen. Yes, what you have, now you have 0.28% marked for rejection. This is green, which indicates that everything is okay. And 4% are matched. Yes, I will do scaling 2 more times. Note one thing, that I am working completely on defaults. Not always you can work on defaults. And look that the completeness of the low-resolution data is great. To 224 angstrom, we have 100% completeness. Yes, and low resolution are very important. Chi-square are perfect, and you have anomalous signal. It's not very strong, but it's enough to solve structure. And you cannot expect very strong signal from surface. Yes, it will be always relatively weak. So you see that this is the end of the HKL2000. We have HKL, F, and sigma. So now we can check by using HKL3000 how good are these data. Yes, and we are going to structure. And first thing, you see that it have chosen automatically. It have chosen 2 molecules in asymmetric unit with the solvent content 30, and we will try to put 1. I mean, we know that it's 1, and the solvent content is 65. So which is little high. So you see that it's always, both things are positive. They are on the border, and this is the reason why we have to engage our brain. I mean, it's not only clicking. From time to time, we have to engage our brain.
And the solvent content was it solvent content calculated based on your sequence that you put in the
yes.
first in the project window?
Calculated on the base of the sequence and 2, and when I change using estimate, it was calculated again with 65 for 1 molecule in asymmetric unit. So if you would put, I can do that again. Yes, if it's 1, it's 65. If it's 2, it's 30. If it's 3, it's 0. Yes? So I am coming back to 1, and we have 1. So that so this is 1. Data analysis shows you that you have the relatively strong anomalous signal. You can try to find sites. Yes, the sites. To look for sites, it may take more than 10 seconds, just because the signal for sulfur is relatively weak. So you see that I hope that we will find that really fast. But basically, maybe, Piotr, what do you think? Maybe we should, because I am talking half an hour, or little less than half an hour. So you see that here we have the best is 3014, which should be enough to solve the structure. So I can click finish, and at that point we are not looking anymore for sites. We can look on sites and manipulate size, and we can go to phase and check the handness, check which enantiomer is really really the right one. And as you see here, you have substantial difference between two enantiomers, which indicates that sites are correct. Yes, if there is no difference, it means that the map looks bad for both enantiomers. If you have substantial difference in contrast of the map, it's very good indication. So we did that, and we can phase. And phasing is relatively fast. So if you will allow me to have 3 more minutes, we will have the map, and we can build the model during the discussion. Is that okay?
Yeah, go ahead. Yeah.
Okay, so this is phasing. Figure of merit, phasing power, quite reasonable phasing power. Yes, and solvent flattening, automatic solvent flattening. Okay, and this is the map. Yes, we have disulfide bonds here. Yes, disulfide bonds here, and relatively good map. Yes, I would say that I can see maybe not holes in the aromatic rings, but dips at least in some aromatic rings. But I think that the map is, I would say, even great. Yes. So you see that the only thing what we can do now is to go to the model building, and I am just clicking build the model. Yes, that this is the only thing what we can do. Yes, and we will see what will happen with the model. And here with 1.9 resolution or 1.8 resolution, I am using ARP-warp. Otherwise, we would do something more intelligent. But you see, in build cycle 1, 94% was built. In the end of the main cycle 1, we basically have 92% of the protein built. And here you see the secondary structure after everything was built, and we can, and with dummy atoms included, you have R factor 23%, R free 25. And we are doing some refinement automatically and next building. So you see that we are already in quite good shape. And this, I do believe, opens the field for the discussion. I will display after the first cycle is finished. I will display the model from the first cycle. And it's not perfect. You have still a lot of dummy waters, but it's reasonable. Yes. After first cycle, it's reasonable. I would say that at that point, if I would be at the synchrotron, I would say structure is solved. Yes.
Where was this? So was the data for the sulfur collected at the synchrotron, or was it on this zebra?
On the machine, screen machine, Rigaku screen machine, which we had here, and actually this mercury detector was optimized for small molecules. So everything worked against of the rule. So this was just to show that from any instrument, and this is my advice to you, is not to accept the instrument if you cannot solve structure from surface. So if
was it copper or was it chromium? Was it chromium rotating
no,
out?
It was copper.
Copper, okay.
Yeah. I mean, you see that here. Now, chromium, it would be too easy. I would be ashamed to show that here. Actually, now with HKL2000, we can solve basically on any instrument. We can solve structure from sulfurs, and we did some optimization for Rigaku instrument.
The question about mosaicity, from your experience, what is the upper limit of mosaicity that could yield?
There is upper limit. Yes, I mean, you have to have crystal. Yes, but we have solved structure having 3.5 degree mosaicity. Yes, and what I shown you before on this here on the slide, you see that here it's not that you have high mosaicity. You have high mosaicity, but several crystals in the beam. And this is the problem, that you have several crystals in the beam. That, for instance, here you have 2 crystals in the beam. Here you have probably 3 or 4. And this is just poor freezing. Yes, or proof, or poor, I shouldn't use word freezing. Poor cryocool. It could be done much better. People could do much better job. Yes, but you see sometimes you have one crystal. Yes, you have just one crystal, and you have to solve this.
Right. Another question was in terms of optimizing the oscillation range. Yes. What is your golden rule for setting up the ideal oscillation range when you're collecting data?
So I'm sorry, there is no golden rule. The golden, what we are trying to do, and the strategy helps in that, is that you would like to get as much as possible from single crystal. So the ideal situation is that, let's say you have mosaicity 1 degree, I would put 0.5 degree oscillation range. yes? If I would have 2 degrees mosaicity, I would put 1. So you see that you have, so there is some interplay, and it depends on the mosaicity and unit cell. If you have very large unit cell, you have to set, even for low mosaicity or high mosaicity, you are trying small oscillation range, not to have overlap of the reflection. So it depends if you have single crystal or more crystals. It depends on the unit cell. It depends on the mosaicity. And it depends slightly how well your goniostat is working. So for instance, if you have a perfect crystal, sometimes, let's say, the crystal which have 0.1 degree mosaicity. On some beamlines, it's better to collect data with 1 degree oscillation or even 1.5 degree oscillation, because if goniostat is not perfect, the data are poor. The data are poor because your crystal is too good. And you can, if you, maybe Piotr, I will send you some papers which I failed to put here. And in biophysics, we wrote a paper in Biophysics Journal entitled Protein Structure, the Chain of Fortunate Events. And we show that if you have worse crystal, you may solve the structure. For better crystal, you cannot. It depends on the beam on which you are collecting the data.
And in general, so where do you guys collect typically? Do you go to SBC typically?
I have very simple approach to that. For past 8 years, I collect data only on sector 19 and APS, and this is SBC cut. And recently, last 1.5 years, we also collect data on LS cut, which is, I think, sector 22, 21, I'm not sure. This is the Michigan beamlines, life science cut, which are run by Wayne Anderson. And these are the, both sectors are absolutely excellent, but it's not only that they are excellent. The advantage is that even if something does not work well, we can find that in very, very fast, and we can apply pressure on the beam stuff to fix that.
So do you do on-site or you do remote data collection? And for the
remote data collection, we do not. We are going to disinfect. And what is? I mean, this is my philosophy. And you see, surprise, surprise. I think that it's much cheaper to go than to send crystals. And I may explain you why. Because we are using HKL2000. And by the way, anybody who is going to SBC can use HKL2000. And we have immediate feedback. So if we are looking for inhibitors, let's say, or we can visualize inhibitors in a matter of seconds. And if we have binding, we can soak in something else. So we are doing really interactive experiment. We are soaking crystals at the beamline. Yes, and sometimes we are running to the angiochemia club to borrow some, to take some chemicals if we are getting something which we didn't expect. So when you said how many deposits we have learned how to maximize the biological impact of our experiment. So you see that, I mean, you may also look how many papers we produce recently. And this is just because we are trying to maximize every trip. I mean, outcome of every trip. We are not going to often. We are going every 3-4 months. But we are extremely well prepared. We have now, sometimes we are taking 7 dewars with us, or we are shipping 7 dewars, and we are taking some crystals in trays. So our...
How do you ship trays? Because we used to take them on the
No, we are trays to the car.
Oh, in the car you drove, okay.
So you see that some people are flying, some people are driving.
Okay. So any other questions from the audience? Do you guys have any other questions? If you do, just type them in the messenger in the chat window, and I'll ask Wladek if you have any other questions. Okay. And the HKL processing remotely wouldn't work at this point, right? I guess.
Processing remotely will work without any problem. It's not the problem of processing, and some people...
It's just modifying conditions, right?
I mean, from time to time, we were doing things remote, very rarely. You see, sometimes you are getting crystal, you have advanced competition, and in that case, we are sending the crystal, or we are sending one person with the crystal. I mean, it depends. If we have competition to the structure, we are doing that. I mean, we know that competition.
Another question was about the statistics for the data processing. Is there a single place after you show this pipeline to look at the map that you can look and get all the statistics from?
I mean, yes. Just a second. Okay. So you see that you have. Okay. So this is the final map. Yes, and you see in final model. And you can look at Ramachandran, which is more or less okay. You have still something to fix, which is good, yes? I mean, it shouldn't be too good, yes, because, so you see that here it's not perfect, so.
But the statistic for the data set itself, like, you know, something that you could at the end take and put in the table.
You can go to report, yes, and you can click report, and you are getting everything what is necessary for publication, plus more things, yes. So you have here the unit cell, space group, mosaicity range, here the information about processing, site information, here some other, you are getting more redundancy, I over sigma, you are getting more when what is necessary to publication, because, I mean, here is redundancy, you are getting all other things, because sometimes you cannot solve the structure and you would like to look at that very critically. So you see that it's some uniform report. You have here also, this is not, on this computer it does not work. We have publication tab. And publication tab produces a C file, which is almost ready for a paper. So we can, if we would like to publish structure notes, but I discourage my people to publish structure notes. And so far we didn't publish. If we would like to publish structure notes, we can get the C file with all information. We can get part of the paper written. I mean, methods can be written automatically. Yes.
I have another question here, Wladek, about cutoffs by I sigma. And the person is asking if they're using HKL2000, they're getting different statistics, let's say in comparison to XDS. with HKL2000 at I over sigma, they're getting certain resolution. They go back to XDS, and at the same resolution, the I over sigma will be, let's say, 4. Well, why is it such a big difference between this and other packages? And what is the recommended use of resolution cutoff from your experience in the structural refinement?
First of all, I do not run other packages, but I can tell you what is the difference. The difference is how well you estimate sigma. Yes? How well is your sigma estimate? We have found one thing, that if you will look at the structure solved by, if you are looking for all PDB deposits for the last 2 years, HKL is more or less 60%. If you are looking at the structure solved by SAT, single wavelength anomalous diffraction, which requires the best data, so 90% are solved by HKL. So this is the only thing what I can say. I mean, it may depend that that error density for a particular detector is not set correctly, and in the end of the log file, we are showing what is the error density, and should we, I mean, in the new version, should we change the error density inside? And you see that if you will go to site configuration now, in advanced, you can change error density. Yes, you can override the error density, which is in the by putting here the different error density and reprocess the data. So you see that it may be related to the fact that error density is underestimated or overestimated in various packages. But basically, when we, some of this data, as you may look at the deposits, on our deposits, it's something which we have done for people. And usually, they use some other packages, and they couldn't solve the structure. And for that reason, these structures came to us, or this project came to us.
Okay. Do you guys have any further questions? If we don't have any further questions, Wladek, I think I'd like to thank you for participation and for the webinar. And if there are any questions, thank you again. And if you guys have any further questions, you're welcome to send me an email, and we can relay it to Wladek as well. And any closing remarks? Anything else you wanted to say to close the session? Or
no, I would like just to say that thank you very much for inviting me. It was really a great pleasure and a great opening of the new year. And I wish everybody many happy structures with HKL.
Thank you very much, and thank you from everybody else as well. Thank you. Goodbye, and we'll see you guys at the end of February. And please visit the website sbgrid.org for information about other upcoming events. Thank you. Panie Władku?